welcome to our today's lesson. I'm your instructor, John Gekonyo. Today we shall be looking at numerical analysis, and our topic of discussion will be solution of algebraic and transcendental equations. So our key objectives that we shall look at are to be able to differentiate between algebraic and transcendental equations, how to find solutions of algebraic and transcendental equations. So we first define what is an equation. An equation of the type fx is equals to 0 can take two forms, either algebraic or transcendental equation. So an algebraic equation is a polynomial that take any given form. And in this case, we have an x to the power n plus an minus 1 x to the power n minus 1 all the way to a1x plus a0, where an minus 1 all the way to a1 are constants. For example, we have x to the power 4 minus 4x squared plus 5 is equals to 0, and 4x squared minus 5x plus 7 is equals to 0, and a cubic function 2x cubed minus 5x squared plus 7x plus 5 is equals to 0. So those are some few examples of algebraic equation. So a transcendental equation is one in which it contains either trigonometric ratios, exponential, or logarithmic function. For example, we have an equation x is equals to cos x, which has a trigonometric equation, trigonometric ratio, and we have one that has an exponential function, and we have one that has a logarithmic function. So there are ways in which we can find solutions to either algebraic or transcendental equation, and we have two common ways, and one of them is the direct method. So this method is used to find solutions of a given equation in the direct process, and some common methods that are classified as direct methods are synthetic division, use of remainder theorem, and factorization method. So note that by using direct or directive methods, it is possible to find exact solution of any of a given equation. So then we have the indirect methods. So the methods simply aims to approximate the roots. So by using indirect method, which are also called iterative methods, it is possible to find an approximate solution of the given equation, and also it is possible to find a single solution of a given equation at the same time. So some common methods that can be categorized as indirect method or iterative methods, we have the bisection method, we have regular Farsi method, and then we have iterative method, Newton-Raphson method. So these are just but a few. We have others like second methods and many others. So our methods of interest are the four. So when we refer to roots, what do we necessarily mean? So a number alpha is a root of fx is equals to 0 if f of alpha is equals to 0. That means the value of the function at the given value alpha is equals to 0. And the first derivative of f alpha is not equal to 0. Then we can write the function fx as fx is equals to x minus alpha gx, where gx is any given form of a function. So we shall start with our first method. And before we can look at that, there's something that I want you to note, that there may be many roots of a given nonlinear equation, but we will seek to approximate only one real root. So we start with our first method. This is the bisection method. And as the name suggests, the approach will involve trying to narrow down the interval under which our root lies. So what we do, suppose we start with an interval for which fx changes sign. Then we have the interval until the interval converges to the root. So what we start with is we select two values or real values a and b, and we find the corresponding values of the function fx for fa and fb, such that one of them is positive and the other one is negative. And in this case, we can have fa being positive and fb being negative. So we try halfway, and this gives us our first approximation of the root, and then find the corresponding value of f a plus b all over 2. So the process is repeated, and the process is repeated in this form. So here we have our first guess. We guess the first real value that gave us a negative value, and then we guess another value that will give us a positive value. So when we narrow down such that we have we have a plus b over 2. So note that the first interval was this one. Then we have the second one. If f of a plus b over 2 is positive, then we will consider f of a, which was negative, and the new f of a plus b over 2, which is positive. And then we narrow down. As you can see, as the interval narrows, the value converges to the root at that particular point. So this is how you check whether the function or the interval is converging to the root. So what we shall do is this. So with our first approximation a and b, what we do is we have the interval a plus b over 2, and then we look for the corresponding value of f a plus b over 2, and we proceed like that until we have the appropriate approximate of our root. So I want us to look at an example here and see how we can apply the method described to find approximate root to this particular function. So we have a function f of x. We have the function f of x is equals to x cubed plus x squared plus x plus 7 is equals to 0. So this is a cubic function, and here we have a positive last value. And as you can see, the end root is likely to be a negative value. So what we do, we start with our first guess. So we start with our first guess, and we can guess that the root is -1. So we look for f of -1, and f of -1. So what we do is we put -1 at that point. So we plug in -1 into our function and find the corresponding value of fx. So we have -1 cubed plus -1 squared plus -1 plus 7. And we find that the value is 6. So this is our, so this gives us a positive value. So we can guess another value, -2, and see what we shall get. So we look for f -2. So this is -2 cubed plus -2 cubed, squared, sorry, plus -2 plus 7. And we find that the value of f -2 is 1. So we are yet to find a value that will give us a negative. So we can try -3. As we can see that -1 was a large positive value, -2 a smaller value. So it's likely that our -3 will give us a negative value. So we have -3. Squared, well, -3, sorry, -3 squared plus -3 plus 7. And here we find that the value is -14. So there is something I want you to note, that with the bisection method, the rate of convergence will depend on your initial values that you guess. So when the values that you guess are very close to the root, then the convergence may tend to be slow, and that can be proved as compared to when you are dealing with values that are far from the root. So therefore, we can say that the root lies between as you can see, -2 and -3, or simply -3 and -2. So we shall start with the first approximation. So we say that the bisection method will aim to reduce the interval of our first two values. So we start with our first approximation, which will be given by -2 minus all plus -3 all over 2. So this will be our first approximation, and this gives us -2.5. Then we are supposed now to find the value of f -2.5, and what we do is plug in -2.5 into our function. We have -2.5 cubed plus -2.5 squared plus -2 plus 7, and we find that the value will be -4.0875. So the value will be -4.875. So once we have computed the value of f -2.5, our aim will be now to establish our new interval where the root lies. So the root will lie between that positive value that we obtain and the immediate negative, or the negative that you've obtained and the immediate positive. So the root clearly we can see lies between f -2, because f -2 gave us 1, and f -2.5, or simply lies between -2 and -2.5, which give us a negative value. So the interest here is the sign that results from finding. So here this is positive, and here this is negative. This is negative. So this is negative. And this is positive. So this is our new interval. So we have, so our first guess, our first approximation was negative 2.5. And we've seen that f negative 2.5 has given us negative 4.875. So we approximate the second root, and this is how we go about it. So we pick the immediate negative and the immediate positive. So we have negative 2.5 and negative 2. So this is where our root lies. So the root lies between negative 2.5 and negative 2, because negative 2.5, f of negative 2.5 has given us negative 4.875, and then f of negative 2 has given us 1. So we approximate our second approximate of the root. So we shall have minus 2.5 plus minus 2, all this over 2. And this will give us negative 2.25. So we aim to check whether f of x2 or f of negative 2.5 will be positive or negative. So let us check. We have f of negative 2.5, negative 2.25, and this is giving us negative 1.5781. And this is how we go about it. We plug in negative 2.25 into our equation, and this is what we obtain. Negative 1.5781. Therefore, we can easily say that the root lies between negative 2.25, since f of negative 2.25 is negative 1.05781, and negative 2, since f of negative 2 is 1. So the root lies between negative 2.25 and negative 2. So the iteration should continue, and as we can see from our question, we are supposed to find the root correct to 3 decimal places. So we shall observe our approximation. So these approximations, there's one that we obtain from here, and there's one that we obtain from our first guess. And we should do successive approximations and see a point whereby we shall easily check the decimal places, and from there we can tell that the root, the approximate root is this. So let us see other approximations, how they will be. So we have x2. So x3 will be given by negative 2.25 plus minus 2 all over 2. So this is giving us negative 2.125. So f of negative 2.125, which you can check would be negative, and the other approximations, x4, which I would like you to try and confirm, will be as follows. So x4 will be negative 2.0625, and then we have x5, which will be negative 2.0938. So the number of successive iterations normally depend on the condition given. So in our question, for example, in this case, we want to find the root correct to 3 decimal places. So we should do the iteration such that the values past the third decimal places are not changing significantly. So x6, I would like you to confirm this is going to be negative 2.1094. x7, this is going to be negative 2.1016. x8 will be negative 2.1055. x9 will be negative 2.1035. x10 will be negative 2.1045. x11 will be negative 2.1050. So this is what we are supposed to check. So note the third decimal point. So here we have 5. So here we have 3. Here we have 4. So here you have 5. But normally when finding the value correct to a given decimal places, so we are supposed to check the corresponding value. So the interest and what is important is that whatever approximation that you give should be significant in this sense that the absolute error or the relative error should be very small. So if you look at the difference between x10 and x11, so we can see that it is very small. 0.0005. Hence, we can conclude that the root is given by x 11, and writing this correct to 3 decimal places will be -2.105. So our approximation to the root, we can say, is -2.105. So our example here, so this is an algebraic equation, which is a cubic function. So maybe we can try and see how we can deal with a function that has exponential ratios, trigonometric ratios, and exponential function. So we can find the following, we can approximate the root to the following equation, correct to 3 decimal places. So this is our equation: 4 exponential to the power negative x sine x minus 1 is equals to 0. So this is a transcendental equation. Since we have an exponential here, an exponential function, and we have a trigonometric ratio here. So we can write the function fx to be 4 exponential negative x sine x minus 1 and to find our first approximation, we begin by guessing the roots such that f of the guessed values a and b should give us opposite signs. So let us start with a value 0. So let a to be 0. So what is f of a, which is f of 0? So we plug in 0 in our equation. Exponential to the power 0 is 1. So this will give us -1. Then we guess another value, for example, 0.5, f of 0.5. So this is giving us 0.163. 145. So the values that we obtain here are only helping us to tell where the root lies. So this is negative, and this is positive. Therefore, we can say that the root lies between 0 and 0.5. So we can go ahead and find our first approximation. So our first approximation will be, so this is x1, approximation to the root. So since this is the interval, at which our root lies. So we intend to narrow down the interval. So we start with the first approximation. So we have 0 plus 0.5. We have 0.25. And then we find f of 0.25. Something that I would like you to note here. So we are dealing with a function, a transcendental equation that has a trigonometric ratio. So you note that for some values, the standard way in which runners find the trigonometric ratio is through degrees. But I would like you to work with radians, and you can confirm that if you find sine 0.25 degrees, the value that you get is different from what you get when you find sine 0.25 radians. So ensure that you're working with the correct mode if you're using a calculator. So we find f of 0.25 and check whether the resulting value is positive or negative so that we can tell where the root lies. So f of 0.25 and it is given by 4 minus, no, we have a sine 0.25, and I've said that you should work with radian. The value is negative 0.22 929. So this is negative, huh? So this is negative. And we had here a positive value. So B was 0.5, f of B, which was f of 0.5, gave us a positive value. So we can easily say that the root lies between 0.5 and 0.25. So we have our second approximation. So we say that the root lies between 0.5 and 0.25. So this is giving us what? 0.375. 0.375. Therefore, what we intend to do is to check the resulting value of f of x2. And from that, if we get a positive value, then we should know that now the root lies between 0.25 and this. If we get a negative value, then we shall know that the root lies between 0.5 and 0.375. So those successive iterations are supposed to be done until you end up with a value that, according to your judgment, so this depends on the conditions to your question, is the approximate to the root. So the successive iterations that I would like you to try out are as follows. So x3 will be 0.3125. x4 will be 0.3438. x5 will be 0.3594. x6 will be 0.3672. x7 will be 0.3711. x8 will be 0.3692. x9 will be 0.3702. x10 0.3706. x11 0.3704. will be 0.3705. So looking at the fourth decimal place, so this value tends to be greater than, tend to be increasing. So if we perform several iterations, it's likely that this is going to be 0.371 and some other values. So we can confidently say that our approximation to the root of the given transcendental equation is (0.371). It's 0.371. So the method is very simple to apply. Since we start with guessing two values, and then from there we narrow down the gap of the root interval. So there are some advantages to this given method, and we can say that as long as you have your initial values, that is one that will give you a positive value of the function and the other one that will give you a negative value of the function, then the method will always converge. So with every iteration, so the root bracket or the root interval get halved. So you end up with a convergence to your approximate root. However, there are some drawbacks to this given method, and one of them is that if one of your initial guess is close to the root, then the convergence is slow. So if we started with 0.38 and 0.2 something, all those values that are very close to the root, then we'll find that the convergence will be slow. So the change in the successive approximation will be very small. So if a function fx is such that it just touches the x-axis, like this function, fx is equals to x squared, then it will be hard for us to find the lower and the upper guess, because so our two guesses, A and B, should be such that f of A is negative and f of B is positive. But here we find that f of A is, so we cannot have a value that gives us a negative value at that point. We have also another challenge, especially when we are dealing with this inverse function. So if the function changes sign, but the root does not exist, so we may end up with something that is not converging, and also finding your initial guess will be very hard. So I want us now to look at the other method, which we shall use to approximate the roots to transcendental equation or algebraic equation. And this is the Legler-Faltz method. So this method, we choose 2 points, just like the bisection method. We choose 2 points, A and B, such that if we find f of A and f of B, the two values should have opposite sign. And for the purpose of working, there is no given rule that f of A should be negative and f of B should be positive. So you can work with either, as long as one of them is negative and the other one is positive. Hence, we can say that the root lies between the two values A and B. So what we do in this case, from our sketch, let me give you a sketch here. So from your sketch, if this is your function, this one, if this is your function, f of x, if we guess two values, A and B, such that f of A, in this case, is negative and f of B is positive. So what we do in this case is to try and come up with the line or the chord that joins the coordinates A and FA and B of FB. So we take the point of intersection of this line as the approximate to the root of this given function. So successive iterations will be such that A, this chord or this line will tend to the root, and we can easily say that the root is likely to be at that point. So our first approximation is obtained as follows. So the equation of the line that joins the two coordinates, AF of A and BF of B, can be obtained as follows. So let me show you that. So we can say that if you look at this coordinate, and f of A and BF of B, so this is giving us the gradient, and this is how we find the equation of a line. So we can easily express y as a function. We can easily express y in terms of A, f of A, x minus A, and what we have on the right. So our first approximation is obtained as follows. So we set y at 0. So when we set y at 0, then we make x node the subject of our expression as follows. So this So what we had at this point was y minus f of a. So we set y at 0. Then making x not the subject of our expression. So this will give us our first approximation to the root. If f of x naught, the approximation that we've obtained, is either less than 0 or greater than 0. So we shall have two cases here. So case 1, when f of x naught is less than 0, and we found that f of a is less than 0, and f of b is more than 0, or the other way around. We say that there is no given rule in which we should have f of a to be positive or to be negative, and f of b to be positive or negative. So if we know that f of a is greater than 1, for example, and f of x naught is less than 0, then we can easily say that the root will lie between a and x naught. The other way is true. If f of b is, if f of b is less than, is less than 0, and what we obtain, f of x naught is positive, is negative, then we can tell that the root lies between a and x naught and b. So in order to obtain the next approximation, so we normally replace x1 with b. In this case, when our b and x have the same sign, so if x naught and b have the same sign, so we shall replace with our approximation that follows. If x naught and a have the same sign, so we shall replace with the other guess. So our next approximation will be x1, and this is how we obtain the next approximation. So you note that from our arithmetic workout, so this is not changing, but the replacement here, that is of fa and a, depends on the sign that you obtain from x node. So the second case, this is how I was explaining. So if x node is greater than 0, and assuming that our fb is less than 0, so we can comfortably say that the root lies between b and x naught. So our approximation will therefore be x naught fb minus b fx naught fb minus fx naught. So if fx1 is equals to 0, then we can say that that is the root of the given equation. Otherwise, we should repeat the iterations until we get the desired approximation to the root. I want us to work out an example in this particular case using the regular false method. So this is how we shall. So we have f of x is equals to x cubed minus 2x minus 5 is equals to 0. So the function is a cubic function. And we can say that this is an algebraic equation. So what we can do is to start with our first guess to our equation. So we guess two values such that f of a, so we guess two values a and b such that f of a is negative or positive and f of b is positive or negative. So the key thing is to ensure that the values from the value of fx from your two guesses will have opposite sign. So we have this f of, so let us start with our first guess. And we can guess a is equals to 2, and we look for f of 2. So what we do is we put 2 here in our equation. And then we should obtain the corresponding value. So in this case here we have 8 minus 4 minus 5. So that is giving us negative 1. So we consider another value b. And b, in this case, we can consider 3. Then we look for f3. So we have 3 squared, 3 cubed minus 2 into 3. So we are supposed to plug in the guess values into our function and then find the corresponding value. And then note the sign, because that is what is important. So this will give us what? So this 27 minus 6 minus 5. So this is 16. So this was what? This was negative. And then this is positive. So we can easily tell that the root lies between 2 and 3, because the two values, f of the two values will give us, is giving us opposite sign. So if we have a function f of x, then we know that 3 is somewhere. So if this is 1, 2, 3, 3 is somewhere at this point, and 2 is somewhere at this point. So this function will definitely cut our x-axis somewhere in between that, if we assume that this is our function, x cubed minus 2x minus 5. So the aim will be to narrow down, because negative 2 is giving us, 2 is giving us a negative value here. And 3 is giving us a positive value, 16, up there. So the aim will be to narrow down this gap until we converge at that point. So we know that approximation using Legler-Fast method are given as follows. Once you have the two values a and b, so our first approximation will be given by a minus f of a all over fb minus fa b minus a. But since we shall be replacing a and b depending on the sign of the corresponding approximation to the root, so it is better to work with this. And how do you easily tell how to which to replace with what? So once we have our first approximation to the root, so it is important to note our first guess and what was the corresponding f of them. So we start with, so we had 2, and f of 2 was -1. And then we had 3. F of 3 is 16. So once we note that, we know that, so this is A. And this is B. So A represents the negative, because we have -1, and B will represent the positive or the lower value. So the root lies between 2 and 3. So our first approximation x1 will be obtained. So A is 2, f of B is 16, B is 3, f of B is what? F of A is 2. No, it's -1. Then we have this all over FB. This is 16 minus f of A, -1. So the approximation, so our first approximation would be 2.0588 235. So this is our new approximation. To know what to replace here as we converge to the root, we are supposed to look for f of 2.0588. So we look for f of 2.0588. And this is giving us negative 3.908. or 0799. And this is negative. So we can easily tell that the root lies between what? Between 2.0588, which is giving us a negative value, and 3, which is giving us the positive value. So we replace A with 2.0588. So we always consider the immediate interval that we have found. So our new A will be 2.0588, and the B is still 3. So we go to our second approximation, x2. So we shall have A 2.0588, because if we replaced A with this, then we multiply that by FB, which is 16, minus B f of A, this is 3 into negative 3.9 08. This all of FB is 16 minus FA as per formula is negative 3.908. So our x2, our second approximation, will be 2.08126. So once we have our second approximation, so we shall repeat the same procedure as we've done, and this involves looking for f of 2.08126. So this is giving us negative 0.1472. And to find or to calculate f of 2.08126, it is very easy. We plug in 2.0126 into our expression and then find the corresponding value of fx. So this is giving us negative 0.1472. And since it is negative, so this is our latest negative value. So we shall consider this value, and our latest positive value for fx, which was given by 3. And we can say that the root lies between 2.08126 and 3.0. So from our sketch, we can easily say that the interval between the two values, if this is our Cartesian plane, 0, 1, 2, 3, if this is the value of x, 2.08 is somewhere at this point. So we are still converging to the root. So you note that in some cases the rate of convergence may be slow, and in some other cases the rate of convergence may be very fast. So the following approximations, which I would like you to try out, are approximation to our root. So we had x3, x4 will be, so we use our formula in each and every case to find these approximations. So x4 is 2.08, no, 2.09, 274, and x5 is 2.0896, x7, no, x5 is 2.0938, x6 is 2.0943, x7 is 2.0945, 44. So we've said that the number of iterations that you make normally depend on the question at hand. So in this case, so like us to find the root to this question, correct to 4 significant or 5 significant figures, and with that we can comfortably say that because writing the values correct to more significant figures, for example, x6 is 2.094305. So this is 2.094460. So correct to 4 significant figures. We have or correct to 5 significant figures. We have 2 points. So let me write this, correct to 5 significant figures. We have 2.0945. So the method can be applied to other forms of equation, like the transcendental equations, both those that involve trigonometric ratios and those that involve exponential functions. So the other method which we will try and discuss next time will involve the iteration method and the Newton-Raphson method. So I'd like to thank you for that time that we have had together.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.